Let me welcome you all to the 46th webinar of the Graduate Program in Physics of the Federal University of Pará in Amazônia, Brazil. I ask everyone to kindly leave the cameras and microphones turned off, except for the moment you're going to speak. Questions will be allowed after the webinar, unless otherwise requested by the speaker. The questions can be asked using the chat in both this virtual room and in YouTube. Today, we have the great honor to listen to Professor Lord Martin John Rees, Baron Rees of Ludlow, the 15th Astronomer Royal, appointed in 1995. He's a fellow and former master of Trinity College in Cambridge and president of the Royal Society between 2005 and 2010. Professor Martin Rees is a member of many foreign academies, including the US National Academy, the Russian Academy, the Japan Academy, and the Pontifical Academy. His main astronomical research interests have been galaxy formation, cosmic jets, black holes, and gamma-ray bursts, along with more speculative aspects of cosmology, in particular, whether we live in a multiverse, and the prospects of detecting extraterrestrial life. In addition to his research publications, he has written many general articles and 10 books, most recently On the Future, Prospects for Humanity. Professor Martin Rees has received numerous distinctions, among which I can mention. In 1984, the Denny Heinemann Prize for Astrophysics, jointly by the American Astronomical Society and the American Institute of Physics. In 2003, the Albert Einstein World Award for Science by the World Cultural Council. In 2004, the Michael Faraday Prize by the Royal Society of London. In 2005, the Crawford Prize by the Royal Swedish Academy of Sciences. In 2012, the Isaac Newton Medal and Prize by the Institute of Physics in the United Kingdom. And 2020, the Fritz Zwicky Prize by the European Astronomical Society. Well, we are here today to listen to Professor Rees, so that I won't take your time further with this introduction. Professor Martin Rees, thank you very much once again for having accepted our invitation. And from this moment on, the audience is yours.
Well, thank you very much for the invitation. It's a great pleasure to be able to speak to an audience in Brazil. I'm speaking from Cambridge, and this is Trinity College, where I work. And the best student we ever had in Trinity College was this man here, Isaac Newton. And he did some of his most exciting work in 1665, when the university was closed due to the plague. He had to go home, and he famously, according to myth, sat under an apple tree, and when he saw the falling apple, realized that that was the same force that held the moon in its orbit around the Earth. Well, our students have all gone home the last year, but whether anyone will come up with equally great ideas when the university opens up, I've got no idea. But apart from thinking about gravity, Newton thought about space travel. This is an illustration from his book. It shows cannonballs being fired from a mountaintop, and if they're fired fast enough, then they go into circular orbit. The Earth curves away underneath them as sharply as the trajectory curves downwards. And he calculated that the speed that the cannonball needs to achieve is about 25,000 kilometers per hour. Far beyond, of course, what could be done by the artillery of his time. And again, as you know, it wasn't until 1957 that the Sputnik was launched by the Soviet Union into orbit. And this was followed by many other spacecrafts, first men in space, etc. But my talk isn't about space. I'm going to focus on cosmology, which has been on a roll very, very fast since the 1960s. And at that time, there was a renaissance in general relativity, because that's when objects like neutron stars and black holes were discovered, where general relativity was not just a tiny correction to Newton, but really was crucial. And I was a student in the 1960s, and there were some very strong groups. The inspirational figure in the United States was this man here, John Wheeler. And in the UK, we had two people, Roger Penrose, who's still alive, aged 90, and Dennis Sharma, who sadly is not still alive, who was a great coach as well as a great player, and he had a large number of students, and I was one of them. And in the Soviet Union, a lot of the work was done in parallel by a group headed by the great Zeldovich. Sadly, collaboration was limited in the depths of the Cold War, but we hugely admired all that group managed to achieve in parallel with those of us in the West. It was all collaboration rather than competition. And the 1960s really saw the emergence of cosmology as a genuinely observational subject. The standard models for a homogeneous Big Bang universe were known since the 1920s, associated with names like Lemaitre and Friedman. But until the 1960s, astronomers had no instruments powerful enough to discriminate among them. Indeed, the steady state theory was being followed by Fred Hoyle, who was a senior professor in Cambridge when I was young. And this is a picture taken in the 1950s showing Fred Hoyle on the left talking to Lemaitre, who was a Catholic priest and the president of the Pontifical Academy, but he in the 1920s had the idea of the Big Bang, what he called the primordial atom. And I guess that's what they're talking about in this picture. Well, at this time, there was really scanty evidence that our cosmos had the crucial properties of these models, large-scale uniformity in particular, rather than having an edge or having a fractal-like structure. But we can now, with confidence, trace cosmic history back 11.8 billion years to a moment only a billionth of a second after the Big Bang. And astronomers have pinned down the universe's expansion rate, the mean density of its main constituents, and other key numbers to a precision of a few percent. We're learning how cosmic structures, galaxies and clusters emerged and evolved from amorphous dense beginnings. And I think that when a history of the subject of science as a whole gets written, this amazing progress, a collective global effort, will be acclaimed as one of the great triumphs, up there with the standard model of particle physics and the genome. So in this talk, I want to give a flavor of this and also touch on some new mysteries which come into focus as the science advances. Well, let's start off with something which is well understood, stars and their evolution. Stars are gravitationally bound fusion reactors, and we know that they burn most of their lives, turning hydrogen to helium, and then the evolution depends on how massive they are. A star like the Sun burns hydrogen to helium and then flares up into a white dwarf, blows off its material, leaves a white dwarf behind. Very low mass stars live even longer, slower lives, but massive stars, as I'll discuss later, may leave neutron stars and black holes behind them, more exotic. But this is something which is well understood. The physics is known. We understand the life cycle of stars, and we can see places where stars are forming. This is the Eagle Nebula, and new stars are even now condensing from interstellar gas. And we see stars dying. This is what the Sun will look like in about 6 billion years when it runs out of hydrogen. It's nearly halfway through its life now. It's got 6 billion years to go. But more massive stars burn their fuel more quickly and have more dramatic ends. This is one of the most famous objects in the sky, the Crab Nebula, which is the remnants of a supernova witnessed and recorded by Chinese astronomers in the year 1054 AD. I'm not sure if there are any Chinese speakers in the audience, but if there are, they will see this records that the emperor's court astronomer reported to the emperor that a guest star had appeared, become brighter than the moon, and had faded away after a few weeks. And in the sky, we see nearly 1,000 years later this expanding debris. Well, these events may seem far away and long ago, but we wouldn't be here if it wasn't for supernovae. And this is why. By the end of a massive star's life, nuclear fusion will have led to an onion skin structure where the hotter inner layers are processed further up the periodic table. You get hydrogen, helium, carbon and oxygen, neon and magnesium, etc. And then the star faces a crisis when it can't get any more nuclear energy out, and this is when it becomes a supernova and flings out most of its material into the interstellar space, leaving behind a compact remnant. In the case of the Crab Nebula, a neutron star, which is seen as a pulsar. And the debris from the star will eventually merge with the interstellar medium, and then new stars will form from it. And this is how the elements of the periodic table are built up. And calculations show that this is going to give us lots of carbon, oxygen, etc., but not very much uranium and gold. And it means that we are stardust. Or, if you're less romantic, we're the nuclear waste from the fuel that made stars shine. And we contain inside us atoms that lived and died in stars billions of years ago all over the Milky Way. And the four people who worked this out are shown here: Margaret Jeffrey Burbidge, Willie Fowler, and Fred Hoyle. And they wrote a classic paper in 1957, which had all these basic ideas in it. This picture was taken actually in Cambridge in 1971, I think it was, when Willie Fowler had a 60th birthday party, and he was a model train enthusiast, as you see, so that was his present. And Margaret Burbidge, she lived to be 100, and this was taken on her 100th birthday, where she's looking at birthday cards. She died about a year ago, but had a wonderful career all that time. So thanks to those four people, and their paper is always called B squared FH, after their initials, we know that our galaxy is a sort of ecological system. I won't go into all details here, but essentially the Big Bang produces hydrogen and helium. That turns into interstellar clouds and stars. And the stars, if they're low mass stars, they stick around. Their lifetime is more than the present age of the universe. But if they are more massive stars, they will end their lives and they'll throw out processed material, which then goes into a new generation of stars. So our galaxy is like a huge ecological system where atoms are processed through successive generations of stars. If we could look at our Milky Way galaxy from, say, 3 million light years away, it would look like this. This is, of course, Andromeda, a tilted disk viewed obliquely, which is the nearest big galaxy to our own. And with a black hole, incidentally, in its center. And here's another galaxy, the Whirlpool Galaxy. Again, this is a spinning disk. And this is a picture which maps out within a certain range of latitudes the galaxies within a few 100 million light years of us. You can see they're not uniformly spread through space. They're clustered together in filaments and big clusters. And we are in a small cluster called the local group, which contains our galaxy, Andromeda, and about 30 smaller members. But how much can we actually understand about galaxies? Physicists who study particles can probe them and crash them together in accelerators. But astronomers plainly can't crash real galaxies together. And galaxies change so slowly that in a human lifetime, we just see a sort of snapshot of them all. But we can do experiments in a speeded up virtual universe. Computer simulations incorporating gravity and gas dynamics can be simulated. Everything in each galaxy exerts gravitational pull and everything else, and we can see what happens. And this is an example of one such simulation of two galaxies crashing together. And as a sort of train wreck, these two disk galaxies will end up as one big amorphous elliptical galaxy. And I should warn everyone that the Andromeda galaxy and our galaxy will have a collision like this in about 4 billion years, which is a long way away, but not before the sun has died. And this is a real picture of two galaxies. And having done lots of simulations like the ones I just showed you, we can understand that in this system, two galaxies have got dangerously close. One has pulled out a tidal plume on the other. And if we were to come back in about 100 million years, we'd find that these two galaxies had probably merged together, as at the end point of the little movie I just showed you. We can also do these simulations making different assumptions about the content of the galaxy, different mixtures of stars and gas and dark matter. And one important thing is that we discovered that we can't really understand how galaxies form and why they have the shape, the morphology they do, without postulating that it's about 5 times as much stuff in so-called dark matter as in ordinary atoms. The dark matter is some kind of particle which has no electric charge and a very, very small collision cross-section, so it doesn't really collide, they just move around, phase mixing as collisionless particles, but they are crucial to the formation of galaxies, and in our galaxy, they make a sort of halo around the galaxy. They're very important. And we can test ideas about how galaxies evolve by actually looking back into the past. And we can do this through looking at pictures like this. This is a picture taken with the Hubble Space Telescope, which shows a small patch of sky, a few arc minutes across. It would take about 50 patches like this to cover the area of the full moon in the sky. But in this little patch of sky, with the Hubble Space Telescope, you can see hundreds of smudges. Each of them is a galaxy, some fully the equal of our Milky Way, appearing so faint because they're so far away. Some of them are more than 10 billion light years away. So we're seeing them when they were young. And so we can test our theories of galaxy formation, our models, not just by seeing if they fit present day nearby galaxies, but whether they fit what galaxies are like 1 billion, 2 billion, 3 billion, 4 billion years ago. And so that's how we have some confidence in how galaxies form. And we can see very far away. This object, you can't quite see it here, is one of the brightest objects in the sky, which has a spectrum, and this is its spectrum. This is a tracing of the optical spectrum, and the important thing I want to note is that the strongest line is the line of hydrogen Lyman alpha, which is normally at 1216 angstroms in the far ultraviolet, but in this case, it's stretched to more than 10,000 angstroms, the infrared up there. It's stretched by a factor of 8.1. by the redshift of this object. So we're looking very far back when we look at objects like this. This object, incidentally, is not a typical galaxy. It's what's called a quasar. It's an object where all the light from all the stars is outshone by light from the center, which comes by a more exotic process, from gas swirling into a massive black hole. And that excites all the gas, and that allows us to get an emission line spectrum of this object in a way we can't for normal galaxies. So lurking in the center of this system, there is a black hole, and this is a simulation of a black hole and gas swirling around and making magnetic fields around the black hole is responsible for the energy which makes quasars so bright and therefore so important. Our own galaxy, incidentally, harbors in its center a black hole of about 4 million solar masses. And this picture shows zooming in on our galactic center. And right in the middle of it, this shows a movie of the stars taken over about 10 years. And these stars are moving at several thousand kilometers per second. They're orbiting around a central mass, which we now know is the black hole. And this is a picture that got huge publicity. This is a millimeter wave picture of the black hole in a galaxy in the Virgo cluster called M87. This black hole weighs about 6 billion times as much as the sun, and more than 1,000 times more than the black hole in our galactic center. It can just be resolved by, this is called the Event Horizon Telescope, which consisted of linking together data from about a dozen telescopes around the world using the Earth's diameter as a baseline. This was a huge logistic achievement, and it at least shows some evidence that there is some sort of dark region in the center, which modeling suggests is indeed the black hole. So by looking at these very distant galaxies and the quasars, we can look back to when the universe was about a tenth or less of its present age. But what about the earlier universe, before any galaxies came into existence? Here, the first key evidence came again in 1960s. When these two gentlemen, Penzias and Wilson, they discovered that intergalactic space wasn't completely cold. It was heated to about 3 degrees above absolute zero by microwaves, which were annoying background in their detector, but was realized to be, in a sense, a relic of the early universe, the afterglow of creation, as it were. And this was firmed up when observations made later at other wavelengths showed that this background radiation had a spectrum of an almost exact black body, which is what you would expect if it had been produced when the entire universe was hot and dense, like the inside of a star, when all the radiation rethermalized, and then as the universe expanded, the radiation cooled, the wavelength stretched, but it fills the universe, it's got nowhere else to go, and it's now pervading all of space as this microwave background. And this has been an important input into developing the sort of time chart, which has been the basis for our understanding of the universe, really for the last 40 or 50 years. This shows time upwards, and the radiation that is observed has been traveling uninterruptedly through space since the temperature, which is now 3 degrees, was 3,000 degrees. Above that time, the the universe was opaque, like the inside of a star, and the radiation was thermalized, but from that time, it's been traveling freely. So it gives us information about the universe when it was 1,000 times more compressed and when it was about 300,000 years old. We also have pretty convincing evidence that this simple model was relevant when the universe was just a few seconds old. And the reason for that is that you can work out the nuclear reactions which would happen as the universe cooled down from, say, 10 billion to 1 billion degrees, which happens in the first seconds and minutes, and the proportions of hydrogen, helium, and deuterium and lithium which are produced at that time match what we observe. Some people, like Lemaitre, thought all the elements were made then, but of course, as I've explained, the rest of the elements are made in stars in the universe, but the ratio of hydrogen and helium was determined mainly by what's happened when the universe was a few seconds old. So I would say we can believe in this back to a second with as much conviction as you believe anything a geologist or geophysicist tells you about the early history of the Earth. We have really good quantitative fossils. And indeed, I think we can probably believe in this back to a nanosecond or less. More about that later. But first, let's address an issue that might seem rather puzzling. Our present universe manifests a huge range of temperatures and densities, from blazingly hot stars to the dark night sky. People sometimes worry about how this intricate complexity emerged from an amorphous fireball. It might seem to violate the second law of thermodynamics, which describes an inexorable tendency for patterns and structures to decay or disperse. But the answer to this paradox lies in the force of gravity, which enhances density contrasts and doesn't wipe them out. So any patch that starts off slightly denser than average would decelerate more because it feels extra gravity. Its expansion lags further and further behind. It eventually stops expanding and separates out. Many simulations have been made, and this one I've just shown shows one example where the expansion has been subtracted out, so it looks the same scale, but this shows how structures form. Right. And one important point is that we can do calculations putting in the early universe not just any random fluctuations. There've got to be some fluctuation, because if the universe started out completely smooth, it would now be just cold hydrogen and helium and no stars and no people. But we have, from the Planck spacecraft and others, evidence that the microwave background isn't completely smooth. On the so-called last scattering surface at 300,000 years, the temperature varies from place to place by about 1 part in 100,000. And this is a projection. You've seen maps of the world projected this way. This is a map of the sky, a sort of inside-out version, showing the same thing. And what's remarkable is that if you feed in fluctuations like this and run your simulation forward, you end up with a universe that is like what we observe, in the sense of having galaxies of about the size we see, clustered in the way they are. And this is a remarkable triumph of the model. And it's quantified here. What this shows is the root mean square fluctuations in the universe today as a function of scale. It's smooth on large scales, rougher on small scales. And we have various lines of evidence, clusters and galaxies and intergalactic clouds, etc. They all lie on the line, which is what you would expect if you put in, as your initial conditions in the simulation, fluctuations with a spectrum of amplitudes a function of scale, which agrees with what is observed. And this is a really remarkable achievement. And incidentally, there's something even more remarkable. if you analyze, do a sort of Fourier analysis of these fluctuations and see on what scales the amplitude is largest, just like on an ocean you may see how much amplitude is in waves on different length scales, you get a picture like this. This shows the angular scale on the sky on the top of the picture, there's a big peak at about 1 degree, and on smaller scales than that, there are some waves. And the reason I show this is that the dots show the data, and the curve shows the best fit theoretical model, because this shape, what I call the elephant diagram, was actually predicted. The biggest peak corresponds to a sound wave which has had time to make a quarter of a cycle before decoupling in the first 300,000 years. That's a big peak. And then the higher ones are oscillations which have had time to oscillate 2 or 3 times before the matter and radiation decoupled. So this is, again, corroboration that we do understand what happened in the early universe. Back to 1 second. And I would say that we can, with confidence, go back to probably a nanosecond. The reason I say that is that that's the time when every particle would have about 50 GeV energy, about the energy that can be produced in the Large Hadron Collider, the big accelerator at CERN in Geneva. So after the first nanosecond, the postulated conditions are within the realm of experimental test. So I would say we should take seriously back to not just 1 second, but 1 nanosecond. But that's not far enough, because many key features of the universe, like what caused the fluctuations, why does the universe expand the way it does, why does it contain the observed mix of atoms, radiation, and dark matter, the answer to those questions lies even earlier, not just in the first nanosecond, but in the first tiny, tiny, tiny fraction of a nanosecond. And here, the physics is not so well understood. And so let me put in a hazard sign to say that the physics of this very early universe is speculative, because it's not battle tested by experiments. But according to a popular theory, this shows the same sort of time chart focusing on the earlier bits. According to this popular theory, the entire universe emerged from something of almost microscopic size and then inflated exponentially in the first 10 to minus 36 seconds. And to put this in perspective, when the universe was a nanosecond old, and I said that's how far back we can confidently understand the physics, the entire observable universe will be the size of the solar system. But if we go back to the inflationary era, the entire observable universe will be the size of a tennis ball and would have emerged from something smaller still. So this is a theory which does explain many features of the universe. It explains the geometry of the universe, and it incidentally can explain the fluctuations which I showed, which are spread across the sky, as seen by the Planck spacecraft, and which turn into galaxies and clusters. They could be quantum fluctuations when the entire universe was microscopic size. So this is a fascinating idea, but it's still something which we should say is not fully confirmed. 20 years ago, cosmologists had a big surprise. It doesn't change anything I've just said, but it does alter our perspective on the far future. It was by then well known that the gravity of dark matter plus baryons plus atoms was only about 30% of the so-called critical density. The critical density is what makes the universe a flat Robertson-Walker universe and tilts the balance between whether it'll go and expand forever or will recollapse. So we have 2 models for the universe, with 3 models here where time goes upwards. The left-hand side model would be one if the universe had a density above the critical density, and it would then recollapse to a big crunch. if the density is below the critical density, then it decelerates in the expansion because of the gravity of every galaxy exerts a force on all the other galaxies, but never comes to a halt. And I think until the late 1990s, most people thought our universe was like the second one. But it turns out that it's like the right-hand side picture, where there's actually an acceleration of the universe and has been for the last half of its life. And this implies that there's a mysterious force which exerts a push rather than a pull, which lurks even in empty space. And this force is very weak, and we don't notice it in our galaxy, even in a cluster of galaxies, but in intergalactic space, it's capable of overwhelming the integrated gravitational attraction between the galaxies. And this is a force which could be explained by what Einstein introduced as the cosmological constant, often given the name lambda, although it could have a more complicated cause. And this, the evidence for this acceleration, the best known evidence came from observing the Hubble law for distant supernovae and plotting out the distance versus redshift for supernovae. But I'd like to point out that if we just had that bit of evidence, which is indicated on the bottom right, we wouldn't be fully convinced. I thought that the strength of the case was greatly added by another argument, and that comes from the fact that the Doppler peak, the big peak in the elephant diagram, it has at 1 degree, that measures a sort of rigid rod scale, the size of the universe when it's 300,000 years old, and the size of that angle is appropriate to a flat universe. If we're in a universe with just dark matter and baryons, where the density would be 30% of the critical density, then the scale on which that big peak would occur would be about 1/3 of a degree, not 1 degree. So that is telling us that the universe is flat, and therefore there must be 70% of mass energy in some other form, some form which is uniform and doesn't cluster. And moreover, that component must have been less important in the past than it is now. It couldn't have been important in the past because it would have stopped galaxy formation. So it had negative pressure, and negative pressure in the Friedmann equations indicates an acceleration. So in fact, just from the knowledge that omega is 0.3, but the universe is flat, one could have inferred the acceleration, and that's, to me, is important corroboration. And just one curmudgeonly point I'd just like to make briefly. This is a familiar pi diagram you've seen, which shows the different constituents of the universe. The dark energy, 70%, and the dark matter, 25%, and the baryons about 5%. Of course, this is used to say that dark energy is most important. But the dark energy is indeed the most important for fundamental physics, because we won't understand it until we understand the gradiness of space itself. It's probably going to need something like string theory to do that. But for astrophysics, it's not very important, because the dark energy wasn't important in the past. It doesn't affect galaxy formation, and it doesn't affect what happens inside galaxies or clusters now, whereas the dark matter does affect all those things. So for astrophysicists, dark matter is much more important than dark energy, despite this pi diagram, although for fundamental physicists, the dark energy is the biggest unmet challenge to our understanding. So let me ask another basic question. How much space is there altogether? How extensive is a physical reality that's within the remit of science? Well, we can only see, of course, a finite region out to our horizon, the biggest distance that light can have traveled since the Big Bang. There's a sort of horizon around us. But that's not the edge of the universe any more than the horizon around you, if you're on a boat in the middle of the ocean, is the end of the ocean. You don't know what happens beyond that. You don't know how much further the universe goes. There are fairly good reasons for thinking that it goes about 100 times further. The reason for that is that if you look as far as you can in two opposite directions, there and there, then there's hardly any gradient. And so if we're in some large finite structure, the gradient is very small, so it probably is much bigger than the part we can see. But it could be hugely bigger. It could be so enormous that all combinatorial options are fulfilled, that everything happens somewhere far beyond our horizon. And we would all have avatars, and maybe some consolation that somewhere in this space there would be an avatar who made the right decision when we make the wrong one, etc. So that's not impossible, but we have no evidence for that, although, as I say, we have some evidence that the universe doesn't have an edge immediately beyond the limit of what we can see. But that's not all. Everything I've talked about now is the aftermath of our Big Bang, the same Big Bang. But it could be that there are other Big Bangs, and there are some explicit theories. This is a cartoon showing a theory of eternal inflation, which Andre Linde devised more than 30 years ago. This is just a cartoon, I should say, but bottom right, this shows our universe, the observable part, going out far beyond. But this could be the aftermath of just one Big Bang, and there could be many other disjoint Big Bangs. And Linde and many other people have shown that if you make certain assumptions about the exotic physics of 10 to 16 GeV, then this is a natural occurrence, that you will get not just one Big Bang condensing from the substratum, but you get many more. So this is something which we have to be open-minded about. And indeed, since it's possible that there are other Big Bangs, then we have to try and see if we can understand which branch of this decision tree is correct. Is it just one Big Bang, or are there many? If there are many, then there's another important bifurcation. It could be that they're all replicas of ours, or they all obey the same physical laws. But some string theorists think that there are many, many possible vacuum states. And so these other universes, as it were, could have cooled down, ending up with different vacua, different lambda, and moreover, different microphysics, different masses for the fundamental particles, a different standard model, etc. And so if there are many Big Bangs, we want to know the answer to that. Is there a variety in the physical laws and constants, or are those all the same? And this is important because if there are many, many possible laws in the different universes, then what we think of as the fundamental laws are just bylaws governing our cosmic patch, as it were. And then we have the question, are we in a typical universe, or are we in one which somehow is special? And this leads to something which is sometimes called anthropic reasoning. The idea here is that some of these universes would be stillborn and sterile because they would not allow any kind of complexity to evolve. And we clearly are in a universe that did allow complexity, including the Earth and everything on it. And so we are in some subset of these. And so if there were the many universes with different laws, then ours is in some sense special. And this is called anthropic selection. Well, Some people foam at the mouth at the mention of the A word, but I think if physical reality is like the right-hand part of this flow diagram, there is a real motivation to explore these counterfactual universes with different gravity, different lambda and so forth, to explore what ranges or parameters would allow complexity to emerge. And quite apart from the anthropic motivation, some theorists find it helpful to develop their intuition, to explore what would happen if the laws or parameters were different from the actual values. It's like there are counterfactual historians, where scholars would speculate on what might have happened if the Europeans had never ventured to South America in the earlier centuries, for instance. And biologists speculate on how our biosphere might have evolved if the dinosaurs hadn't been wiped out. So in that spirit, I think it's helpful to explore what some of these counterfactual universes are like, to see how sensitive they are to particular fundamental constants. And even if you don't like the A word, then I think it's fascinating and instructive to do this. So let me do a little bit of this myself. But having said that, let me just say that some people don't like the multiverse idea and this, because it would render the hope for neat explanations of the fundamental physical numbers vain, rather like Kepler's aim to explain the orbit of the solar system and the planets in terms of the Platonic regular solids. We know that the Earth's orbit is nothing special, except it's in the range that allows life to exist, allowing water to exist and around a stable star, etc. So it would be harder to explain the fundamental laws, but our preferences are irrelevant to the way physical reality actually is. So we should be open-minded, in my view, about the possibility of a fourth and grandest Copernican revolution. We've had the Copernican revolution itself, then the realization that there are zillions of planetary systems in our galaxy, and then that there are zillions of galaxies. But we then may realize that our observable domain, our Big Bang, is a tiny part of a far larger and possibly diverse ensemble. Well, let me just consider some examples of what would happen if some of the laws were different. And I'll think of this as counterfactual history. What about gravity? Supposing that the force of gravity was different, supposing that g, proton mass squared over hc, were a different number. Let me illustrate this by my favorite pedagogical slide. This shows mass upwards and radius horizontally. And as you can see from the numbers, it's a very large scale spanning 10 to the 76 upwards, and a very large scale horizontally. Now, the reason for that is that 10 to the 38 is what you might call the inverse of the gravitational fine structure constant. And powers of that are very important. So let me just explain this picture. The black holes, they're on a line, slope 1, in a mass radius log plot. That's shown there. You can see the proton at the bottom and a hydrogen atom there. And solid objects are on a line of slope 3 going up from the hydrogen atom. Mass going as a volume cubed roughly, and then we have humans, asteroids, and the Earth, etc. But when we get up to the mass of Jupiter, then gravity is becoming more important. We're getting close to the black hole line, and so we then get to the realm of the stars, objects which are not just made round by gravity, but are crushed by gravity. And the Chandrasekhar mass, white dwarfs, is a mass that contains 10 to the 57 particles. And one point to note here is that a black hole with the radius of a proton contains 10 to the 38 protons. And the Planck scale, which is where Schwarzschild radius and Compton wavelength are the same. That is on the left at 10 to the minus 19 proton radii and 10 to the plus 19 proton masses. So this is a nice way to explain all these things. Well, after all that, what would happen if big G was stronger or weaker? If it was stronger, then this scale would be compressed. There wouldn't be so many powers of 10 between the scales where you get black holes and stars. So you get small scale stars, you still get them as gravitationally bound fusion reactors, but they would be smaller and shorter lived. And up to a point, it wouldn't change things very much. Indeed, if you had an even weaker gravity, then you might have a rather better universe, because stars could be bigger and more long-lived, and objects could get bigger before being crushed by gravity. So there'd be more scope for complexity to arise. Gravity is a force that has to be weak in order to allow fairly large assemblage of atoms before it comes into play, but it's not really fine-tuned in any sense. So that's gravity. Now, let me take another number. I talked about the fluctuations in the universe here, and they're about 10 to the minus 5. And that's a number that's normally called Q. And this number Q, which measures the temperature fluctuation, is important because when the bound systems condense out to make clusters of galaxies, etc., they have a binding energy which is Q times mc squared. Virial velocity, square root of Q times c. It's about 1,000 kilometers per second. That's a cluster of galaxies. The biggest scale of nonlinearity in the universe is Q to the 1/2 times the Hubble radius. These are rough figures, but you can easily see why these come out. But let's imagine we had a universe where the fluctuations were of a different amplitude. Suppose they were smaller. Suppose they were 10 to the minus 6. Then we'd have what I'd call an anemic universe, because then it would take longer for fluctuations to condense out, and they would make more weakly bound gravitating structures, and there could be small galaxies, but they might never develop stars and planets, because the first stars that produce heavy elements may shoot them out so that they can escape from gravity, etc. And certainly, if the value of Q were substantially less than 10 to the minus 6, there'd be no complex structures would form. On the other hand, let's go the other way around. Suppose we had a universe with a Q 10 times larger. Then galaxy masses would condense out much earlier at a redshift 10 times larger. And indeed, things like the Coma cluster, which are condensing out now, they would condense out at a redshift of 10, and they would then turn into huge disk galaxies. They'd cool on microwave background, and there'd be huge galaxies with orbital speeds of 2,000 kilometers per second, and they would by now have aggregated into clusters that were even larger. So there'd be a larger range of nonlinear scales than their actual universe. And this would be certainly a more interesting universe for astronomers, and is one that we could perhaps live in. The only disfavoring feature is that stellar systems would tend to be more compact, more close packed together, and that might make it harder for planetary systems to remain unperturbed for billions of years. But this universe would be more interesting. So again, there's no particular tuning of Q, but there is an upper limit, because if Q was more than 10 to the minus 3, then you get monster overdensities, 10 to the 18 solar masses, condensing out at recombination time, producing huge black holes. So the universe would be too violent to allow stars and galaxies at all. And incidentally, if creatures could exist in this universe, they'd find it harder to do cosmology, because the reason we can do cosmology is that the assumption of a homogeneous universe is a good one, because the largest fluctuations are small on the scale that we can observe. And so we can consider a smooth out universe. Just like if you're on an ocean, the biggest waves are in general smaller than the horizon distance. But if Q were 10 to the minus 3 or larger, then it would be harder to define a mean density. It would be more like being in a mountain landscape than on the ocean, in this one dominant feature could affect the entire view. So the simple models wouldn't apply in this model. So the I mentioned that the gravity isn't finely tuned, but has to be weak within a certain range of maybe 3 or 4 powers of 10. And Q is not finely tuned, but has to be probably between 10 to the minus 6 and 10 to the minus 4. And lambda, of course, if that's what causes a dark energy, that has to be very small. It mustn't dominate until galaxies are formed. But if Q were larger, then you could tolerate a larger lambda. I won't go into that. But let me go into the third thing and talk about the microphysics, because, of course, as we know, chemistry depends on the periodic table, and the periodic table depends on having supernovae, of course, but it depends on the binding energy of nuclei, looking something like this standard picture, so that two things can happen. First, we can have a stable periodic table, and secondly, stars can get fuel by nuclear fusion. So people, in particular Fred Adams, have explored what would happen if you tweak the microphysics and get different elements, etc. I won't go into that, but I'll take the extreme case, what I call the nuclear-free universe, supposing that there were no baryons other than protons, supposing that no chemical elements could exist, so you had no periodic table. What would the universe be like then? Well, you could have a universe which would, in large scale, look not too different from ours, because stars made mainly of hydrogen and helium, they would contract, Kelvin-Helmholtz contraction, and they contract until they became white dwarfs or neutron stars or black holes. They become white dwarfs if they're up to 5.6 solar masses, that's the Chandrasekhar mass for pure hydrogen, or they become black holes for higher masses. And incidentally, they put out quite a lot of energy in that process. A star contracting to be a white dwarf would put out as big a fraction of its rest mass in energy as a normal low mass star does. And so the universe would look quite bright. But you can still have Jupiter-like planets, because they form from disks just of hydrogen, and you've got hydrogen, so you've got hydrogen bremsstrahlung and hydrogen radiation and hydrogen cooling. But you'd have no chemistry, no rocky planets, and no life, except perhaps, as I put at the bottom, Fred Hoyle's Black Cloud. I don't know if you know Fred Hoyle, who was a writer of science fiction. He wrote a book called The Black Cloud, which was a big magnetized cloud, which was intelligent and was heading for the Earth. And that was his first and best science fiction writer. So you could have that kind of complexity with nothing else. So this is an example of a universe which, in its gross features, stars, galaxies, and even giant planets would look like ours, but obviously couldn't allow complexity. So if we bear the same relation to the actual universe that a marble statue does to a real human being, it would look the same outwardly, but no complexity inside. So well, as I said already, this is Kepler, and he thought that the laws of the planet's orbits were related to the regular solids, and of course we don't know, that's not relevant, and we need, if we have a universe where the laws are different at different big bangs, then what we call the laws of nature are just bylaws, and the actual laws are deeper. Well, is this a scientific theory? Some people say this isn't science, it's just metaphysics. I would say it is science, but speculative science. And it'll remain speculative unless and until we have a theory which can describe the physics at the inflationary stage and which can be tested in our low energy world by either observations or experiments. I mean, if we had a theory and if it predicts the observed numbers of neutrinos and their properties and some masses, etc., then we would take it seriously. And if it predicts Linday's inflation, then we would take that seriously, because it would be based on a theory that's corroborated. And it's important to realize that you don't have to be able to test all the consequences of theory. Take Einstein's theory. We take it very seriously because it's been confirmed in many ways. And because of that, we believe what it says about the inside of black holes, even though we can't observe there. And that therefore means that in the same way, we would take seriously what a theory predicted about the inflationary phase if it had been corroborated by observations and experiments we could make in a low energy world. But we're far from that stage now, and we don't know whether we'll ever get there. And in fact, about 10 years ago, I was on a panel at Stanford University where we were asked how much we would bet on the multiverse concept. I said I was open-minded. We ought to be open-minded about it. But we were asked on the scale, would you bet your goldfish, your dog, or your life? And I said I was nearly at the dog level. I took it rather seriously. And Andre Linde, who was on the same panel, he'd spent more than 25 years promoting this eternal inflation. And he said he'd almost bet his life. And when the great theorist Steven Weinberg was told this, he said he'd happily bet Martin Rees's dog and Andre Linde's life. Well, Andre Linde, my dog, and I will all be dead before this is settled. But my point is, it's not metaphysics. It's highly speculative, but it's exciting science, and it may be true. Well, in my just concluding just a few minutes, I thought it would be better to come back to more routine areas of science. And I wanted to say two things which are really directed mainly to the young people who may be listening, who are thinking about careers in science. And at the beginning of my talk, I said that the 1960s, which was when I started, was very exciting. But I think I wanted to say that what's happening now is even more exciting. The first thing which has happened is that it's possible to do computer simulations which are realistic enough to help us. And in a subject where you can't do real experiments, these virtual experiments are crucial. And N-body gas dynamics were the first areas, but now we can do strong field general relativity, relativistic MHD, do supernova explosions, not for special symmetry, and plasma microphysics to actually understand shock waves, pulsar magnetospheres, and things like that. So there is really huge scope for theorists to have their insights checked by really precise numerical simulations. And of course, great observatories are coming on board. ALMA is already there, and the European Extremely Large Telescope with a 39-meter mosaic mirror is now being built in Chile. James Webb is supposed to go up later this year, and the square kilometer array in South Africa and Australia, vestiges of it are there already and is now being built. But instruments like this are going to be important. But remember that many things can be done with smaller telescopes. For instance, one of the most exciting planetary systems around another star was found with a 22-inch telescope. So there's lots you can do with small telescopes. And so I think it's a very exciting period when we will have empirical data and be able to analyze it much better. And let me give the final word to Edwin Hubble, heavy smoker here, as you can see. And in his classic book in the 1930s, he said, I quote, "Only when empirical resources are exhausted should we enter the dreamy realm of speculation." And we're in a subject where armchair theory is only 5% of the game, 95% is observations, and that's a good motto on which to finish. So thank you very much for listening.
So we thank you, Professor Martin Rees, for this wonderful webinar, and I'd like to ask everybody in the audience to turn on their microphones for a round of applause. Obviously, I mean, when you were speaking, so all the microphones were closed so that you didn't have the sensation that you were speaking to a big audience. So we are more than 100 people. If we compute together the people that are listening from you to you from this room and the people that are listening to you from YouTube. So we already have some questions, but while people get more inspired to further questions, let me give you a panorama of the audience that you have had. So I like to do that because, you know, Brazil is a huge country. And so we had people from at least 18 different federation units of Brazil. So much more than half of Brazil states have been listening to you. So just to mention, from all the regions in Brazil, from north to south, from east to west, right? So from the northern region, from Amazonia, we have, for instance, Pará, Tocantins, Roraima. From the northeast, we have Bahia, Maranhão, Paraíba, Pernambuco, Piauí, Rio Grande do Norte, Sergipe. From center west, Goiás, the capital of Brazil, Brasília, and Mato Grosso. From southeast Brazil, Minas Gerais, Rio de Janeiro, São Paulo. And from the deep south Brazil, we had people from Paraná and Santa Catarina. I know these names are strange to you, right? But so these are the Brazilian states. And not only that, I mean, we had also people from abroad, like people attending you from Cordoba in Argentina, from Chile, from Mexico, and even from close to you, London in the United Kingdom.
Right.
So we had obviously the undergraduate students, graduate students, postdocs, teachers, and professors from our university attending from Belém, that is the capital of the state, but from nearby cities like Ananindeua and Castanhal, but also from very faraway cities like Santarém, that's more than 1,000 kilometers from Belém. So we had also people from universities, institutes, observatories, and research centers from all around Brazil, right? I wouldn't dare to say their names one by one at this moment, but I can tell you that many people from several distant institutes and universities from all around Brazil. Right. So let's move to the questions then, if that's okay for you.
Yes.
So
one point, I'd like to unshare my screen, but I'm worried I may have turned it off completely.
Great. So let's do the following. So you go to that top arrow in the same one that you started from the beginning. So in the bottom, in the middle, there's you click over it, and then it will say stop sharing screen. Did you find that? In the bar? Yes. No, it's yeah. You have to go back to the.
I think I'm I think I may have lost the Zoom completely. That's my trouble.
No problem. Yeah, what I will do is I'll ask the secretary to make you stop sharing. I think they can have it, can do it. Jenny e Jadir, vocês podem interromper o compartilhamento de tela do professor, por favor? Okay, great. So they did it for you. Thank you very much. And in this way, you can see a lot of boxes, you see, in which many people, so we have more than 50 people in the room and around the same amount in the YouTube.
Right. And can you see me?
Yes, we can see you in a small box, but we can see you. Yes, okay, perfectly. So shall we move to the questions now? Okay.
Yes, indeed.
So the first question comes from Rio de Janeiro, from João Magalhães. João, would you like to make the question yourself? If so, please turn on your microphone and start telling us who you are and your question. So since João did not manifest himself, so let me read his question. Yes. So he has written down, so if we could explain and understand why the universe is expanding, would we ever be able to understand if there was anything before the Big Bang? So he's asking about the pre-Big Bang possibilities.
Well, I think the answer is yes, in principle, because, for instance, if we were in a universe like Linde's, then our Big Bang would not be the beginning of everything. And there are other versions where the universe may be sort of cyclic in a sense. So the answer is that we need to have a better understanding of the early universe to have an answer. And the answer may be slightly sort of off field, as it were, because, for instance, Stephen Hawking had a theory where he said that talking about going back before the Big Bang was like saying you're trying to go north from the North Pole. He had a model which sort of closed up in a natural way. So I think there's clearly a mystery now about the first tiny fraction of a second, and it may be solved by something that's rather counterintuitive, rather than just clocks ticking on back before the Big Bang. But there's no agreed theory, I would say.
Okay, so thank you, João, for your question. Thank you, Professor Rees, for your answer. And then the next question comes from Professor Albert Petrov from Federal University of Paraíba in the northeast of Brazil. Albert, do you want to make the question yourself?
Yeah, I want to make a question. This question enchants me about 30 years. The question is the following. Do you see any connection between eternal inflation and the Everett-Wheeler multiverse concept, which arose from the quantum mechanics?
I think they're separate, because you could have Linde's model and still have the Everett model working in each of the Big Bangs. So I think you can have them both. They're addressing separate things, and obviously makes the universe hugely complicated if you have many Big Bangs in each of which is exfoliating, like Everett said. But I think I'm right in saying that you could combine the two. You could have the model of Linde, which actually can be done without assuming quantum gravity, and you could have a version of quantum theory, which was the Everett interpretation. So I think you can have them both.
Okay, so thank you, Albert, for your question. Thank you, Professor Martin Rees, for your answer.
Can I say that's tentative? I can't claim to be a great expert. So try and find someone who's better qualified than me to answer it. But that's the answer I would give.
Okay, Thank you, Professor. So let's move to the next question then. It comes from São Paulo, the state of São Paulo, from São José dos Campos, Odílio Aguiar. So Odílio, would you like to turn on your microphone and make the question yourself?
Yes, but I'm afraid that my question has already been answered. I was asking about the pre-Big Bang scenario. What the professor would think about it.
Yes, I think I've said all I can say about that, really. We just don't know.
Thank you. Thank you for your excellent talk, Professor.
Okay, thank you, Odílio, for your question, and thank you, Professor Martin Rees. Let's move then to the next question. So the next question comes from the center of Brazil, the state of Tocantins, Mateus Pereira Lobo. Mateus, do you want to turn on the microphone and make the question yourself?
Pode ler minha questão, por favor.
Okay, so what
Obrigado.
Mateus has written about the connection between multiverse and time travel paradoxes. Could you say something about that?
Not really. I mean, time travel paradoxes involve some wormhole effects and matter with negative pressure, don't they? So I only don't think I can say anything about that. No, I'm sorry.
No problem, Professor. Let's move then to the next question that comes again from the state of São Paulo, from Manuel Malheiro from Aeronautics Technological Institute from Brazil. Manuel.
First of all, thanks for this fantastic talk, and in fact, very open mind and clearly open possibilities. But I always make a question, is that if you have an extra dimension, okay, that we know that our laws of physics depend on space dimension, as Stefan Boltzmann law, this T to the 4 for this dimension. And so my point is, we know that in physics, when you are in the orbits, okay, planet orbits, you are in 2 dimensions, but we see the effect of a force like centrifugal barrier that does not allow you to go to the center because you are in 3 dimensions. And so my point is, has anyone explored the possibility of have one more dimension, let's put it that way, and try to develop a new cartoon for the expansion of the universe that depend on the dimensions, or no one?
Well, I mean, let me say just 2 things. First, of course, there are very old arguments against a 4th spatial dimension, which is that you then have an inverse cube 4th law for planets, and circular orbits would then be unstable, etc. So that's an argument that goes back 100 years, which is against that. But I would say also that there's a class of multiverse models different from Linde's, where you imagine that you've got 2 3-dimensional spaces or more, which are both embedded in a 4th dimension, what they call the bulk. And so it's rather like, to take an analogy 1-dimensional down, if you have a lot of insects on a big sheet of paper, they think that's their 2-dimensional universe, and they may be unaware of another set of insects on a parallel sheet of paper, if they've got no awareness of the 3rd dimension. And there are some models of the universe which have 2 3-dimensional spaces which are, in a sense, very close together, but that closeness is measured in some 4th dimension, which we can't penetrate or observe.
I see. Yeah, of course, today you have this 4, but I was asking more at the beginning of the universe. To change some of this physics, but
yes.
Okay.
Well, I mean, of course, if some version of string theory is correct, then that has the concept that what we think of as a point in our three-dimensional space, which you
I
may
see.
have enough is a wound-up origami in 5 extra dimensions. So there's very, very complicated geometry, but the trouble is that geometry is on the Planck scale, which is 10 to the minus 33 centimeters, and very, very hard to
I
do.
see.
String theory does involve extra dimensions, but they're all wound up very tightly, so they don't manifest themselves on the everyday scale. But incidentally, since this is a mention of string theory, I think one interesting conceptual possibility is that something like string theory may be correct, but it may be too complicated for the unaided human brain ever to discover that.
I see.
Maybe AI can help, because they work millions of times faster, and just as they can learn to play world champion chess or Go within a few hours by following through millions of games, they may be able to do the geometry and explore all the options in this 10-dimensional space, and decide which is the right one. And so this may be the only way in which we might discover whether a particular string theory is correct.
I see. Yeah, because I always have idea that dark energy is an effect of an extra dimension. It's not something that is in our universe, comes from outside. But okay, thanks a lot for your clear answer. Thank you very much.
Okay, thank you, Manuel, for your question. Thank you, Professor Rees, for your answer. So let's move then to the next question. It comes from Débora Amaral de Campos. Débora, would you like to turn on your microphone and do the question yourself? Tell us from where you're attending and make your question, please.
Hi, it's such a pleasure to talk with you today. I'm Deborah. I'm from UF in the Rio de Janeiro. I have a question. So I'm sorry, shaking. So a nuclear-free universe could have more Jupiters-like planets, right? So it's like, is that means more gas planets? If yes, why?
So I didn't. Could you say that last sentence again?
A nuclear-free universe could have more Jupiters-like planets, right? So is that means more gas planets?
Yes.
If yes, why?
Well, it could have planets like Jupiter form directly from orbiting gas around a protostar, and they are mainly made of hydrogen and helium, and so that they can form whether or not there are heavy elements, whereas the rocky planets, of course, require the heavy elements. So the very hypothetical nuclear-free universe could have stars, and it could also have big planets which formed from a gaseous disk, which is the way that Jupiter is thought to have formed. But what you couldn't have is planets which are made of heavy elements or are rocky.
Oh, thank you.
So thank you, Deborah, for the question. Thank you, Professor Martin Rees, for your answer. And then Mateus Lobo from Tocantins asked again another question. So he's asking if the cosmological constant fully explains the accelerated expansion of the universe, and if so, if positive, do we really need dark energy? And he complements saying, can it be only a mathematical function like many other that rules our universe?
Well, I mean, I think Einstein's lambda, which is a constant in space and time, is indeed the simplest interpretation of what's called dark energy. And indeed, all the data is consistent with that, because the data, as far as we can say, implies that the strength of the dark energy is the same at at all redshifts we can observe. So it could be that it's, in classical terms, fully represented by lambda. But of course, we'd like to go one stage deeper. And as I said in talking to the earlier questioner, we'd like to understand the structure of empty space. Empty space has a sort of graininess and structure, but we think that that structure, which may involve extra relative dimensions, is on the Planck scale. And so to explain why there was a non-zero lambda, we would like to have an explanation in terms of the microstructure of space. And that's a big ask, a big challenge, because that microstructure is on a scale 10 to the minus 33 centimeters. So it's certainly possible and is favored by all the data, I think, that the dark energy is independent of space and time, and therefore, in terms of macroscopic physics and the Friedmann equations, is just the same as Einstein's lambda.
Okay, thank you, Mateus, for your question. Thank you, Professor Rees, for your answer. And then let's move to the next question that comes from the northeast of Brazil, the state of Paraíba. Paulo Sérgio Rodrigues da Silva. Paulo, do you want to turn on the microphones and make your question, please?
Sure. Thank you, Crispino. Thank you, Professor Rees, for the excellent talk. My question is, does the proposal of multiverse imply that before the Big Bang or Big Bangs, there was space-time and only then the laws of physics, different ones, emerged? In this case, by different physical laws, you mean only different fundamental constants or really different paradigms?
Well, I mean, I think, let me say, we don't know the answer because we don't have an agreed and tested theory. But I think the way I put it is that what we think of traditionally as the fundamental laws and the fundamental constants would, in this grander perspective, be sort of local bylaws in our cosmic patch. Our cosmic patch would be bigger than the observable universe, but there would then be a deeper level of laws which would indeed govern the whole ensemble, as you say. But these actual, what we call the constants of nature, the strength of gravity, etc., would be secondary things. And some of the constants may in fact be universal, others may not be. And to give an analogy, Paul Davies gives a rather nice analogy of snowflakes. Snowflakes are very different because the details of them depend on the details of the temperature and humidity in the cloud where they formed and their history. That's why they're all different. But they all have hexagonal symmetry because that's fixed at a deeper level from the properties of the water molecule. And likewise, there may be some laws which are laws at the deeper generic level that applies to the whole ensemble of universes, whereas there might be others which are more sort of environmental accidents which apply only to some of the Big Bangs. This is all speculation, but that's a logically possible view that there's some of the present things we observe may be bedrock universal features of the physical world, whereas others may not be. But we don't know which, if any, are in those two categories.
Well, maybe that's the best you can do. It's only varying the fundamental constants by now, right?
That's right, yes.
Okay, thank you.
So thank you, Paulo, for your question, Professor Rees for your answer. So now a question that comes from the YouTube. So Dinorá Barbosa, that she is at the Brazilian National Observatory, and she has written, still regarding the inflation problem, would it be possible to look for any observational signature concerning bouncing universes or multi-universes?
Well, there may be some, but I think one point is that there are a whole lot of versions of the inflationary universe. It depends in detail on the physics at this extreme temperature corresponding to 10 to 16 GeV. One of the ways in which we can narrow down the range of options is that the different assumptions about the physics make slightly different predictions about the fluctuations. I mean, the fluctuation amplitude Q is not predicted by any of these, the form of the spectrum, the amplitude as a function of scale, isn't. And also, there's another important feature, which is that there are two kinds of fluctuations that can be made in the early universe. One is the density fluctuations, so-called scalar fluctuations, and the other is transverse fluctuations, which are in effect gravitational waves. Different assumptions about the early physics make different predictions about the ratios of those two. And observations of the cosmic microwave background are trying very hard to separate out these two components. You may remember that there was a claim from an experiment called BICEP 2 a few years ago that they had actually detected the so-called tensor modes, which were due to gravitational wave fluctuations, gravitational wave propagating through the universe. And if that were the case, that would have been an important input into our understanding of the early universe, because that would be a new number, the ratio of scalar to tensor, which would have constrained the physics. But you probably know that observation didn't survive scrutiny. And at the moment, all we know is there's an upper limit of some kind to the tensor modes compared to the scalar modes. But that's something we could learn from the microwave background and other features of the microwave background, like deviations from Gaussian fluctuation amplitudes and things like that.
Okay, thank you, Dinora Barbosa, for your question, and thank you, Professor Rees, for your answer. So the next question, somebody has registered for a question, is Edson Nogueira. So Edson, can you make the question yourself? Would you like to tell us from where you are attending and make your question, please?
Hi, good morning, everyone. Thank you, Professor Crispino. Thank you, Martin Rees, for your wonderful talk. My question is related to the fine-tuning problem that you mentioned in your talk, specifically about the Q parameter that you mentioned. And I remember I really don't know how many years ago I read a book that you wrote called Six Numbers, just six numbers, the deep forces that shape the universe.
Yes.
I read it by curiosity because I found very interesting the questions. And there you talk about the number D, which is the number of spatial dimensions, right, in the space-time. And it is argued that if D were 2 or 4, for example, life could not exist, as we know. And I'd like to understand if this contradicts some current theories, for example, some string theories that require 10 spatial dimensions. How does this reconcile with that assertion? And just to finish, I'm very glad that I never imagined that I would be able to ask you directly. So it's a pleasure to make this question.
Yes. Well, in string theory, there are, as you say, extra dimensions, but they are all tightly wound up on a very small scale. So we don't see them, we won't see them directly unless we can probe down this very tiny scale. So it's just like, if you look at a hose pipe from a distance, it looks like a one-dimensional line, whereas really it's got 2 extra dimensions which are rolled up. And so string theory does indeed postulate 10 dimensions altogether, maybe, but only 3 of them are manifest as spatial dimensions in our world, but the rest would be detectable if we could magnify a tiny bit of space and look at it at this submicroscopic detail. But the challenge is that the scale on which we'd expect these things is a billion times smaller than an atom. So it's most unlikely we'll have any direct evidence.
Okay, thank you, Professor. I'm talking from Belém. I'm a student from here, from the PPGF UFPL. Thank you.
Okay, thank you, Edson. Edson is our PhD student in our graduate program. Thank you, Professor Rees. Professor, as I said, so we are going to 1 hour and a half, more or less. So I said I would ask you if we could keep on with the questions, or is it a good time for us to stop, Professor?
I'm happy to go on a bit longer.
Okay, so let's go for a couple of questions and then we close it up, okay? So the next question comes from the YouTube, so Vitória Andrade from Goiás. So she has written in Portuguese. I'll try to translate, and I hope I can understand what she has written. So she said that, so we found ourselves inside systems that are inside systems. You know, the solar systems, and then our galaxy, and then clusters of galaxies, and then the universe, and then possibly multiverses. So it's kind of a hierarchical way of constructing our own knowledge of what we are inside. So would you like to comment on that?
Yes. Well, I think that's certainly true in a sense, but it's not the same as what's called a fractal, where everything is the same on. I don't know if you know what the fractal is. It's something which has a structure, and if you magnify it, then you see the same thing on a smaller scale. Branches of trees obey this quite well. But in the case of the universe, this type of structure doesn't really extend over several powers of 10. We have obviously we have star clusters, we have clusters of galaxies, and then we may have some even bigger scales, but it's not really explained by a single hierarchy where you have wheels within wheels going on, because the physics which determines the different scales is different. I mean, the physics which determines a star is different from the physics which determines a star cluster, which determines a galaxy, which determines a cluster of galaxy, and which would determine a multiverse. So I think it's true that there are these different scales in the hierarchy, but they are each really governed by different physics, I would guess. It's not just that one is a miniature version of the other.
Okay, so thank you, Vitória, for your question. Thank you, Professor Rees, for your answer. So another question from YouTube that is a bit related to this. So it's from Gabriel Jonk from Florianópolis in the south of Brazil. So he says, it seems that we've been finding more structure as we approach larger and smaller distance of the cosmos. Don't you think that we should incorporate an infinite detail hypothesis in our theories from the start? So it's kind of related to this. I'll make a last question. So there's one more question from João Magalhães. João, can you make the question yourself? Then it's going to be our final question, or shall I read it? I'll read it then. Okay, so he has written, considering the idea of that the gravitational force is a warp of space and time, could it get weaker as the universes expand itself? Once this mesh would be getting more and more stretched out and tense. So, Professor, I mean, there are these two questions. Let us make this our final questions. And then if you want to answer them and then make your final remarks, and so we could come to a closure, Professor, please.
Okay. The first one was about should we consider the whole infinite range of scales? I think the universe isn't scale-free in that way, because, for instance, if we talk about the fluctuations in the microwave background, which are the density irregularities from which galaxies and clusters form, they have an amplitude which we can measure on different scales, and they really do smooth out on the large scales. It's not like an ocean where the waves have the same height on all scales. There's a particular range of scales which are important, and then the universe really does get smoother on a large scale. And that's a good thing, because that means that on the very large scales, we can approximate the universe as smooth in our calculations. So there's a particular scale where the early universe has fluctuations, which are important. And that's true, I would say, for most phenomena. They have particular scales. I mean, stars obviously have a particular range of scales, and we understand roughly why that's the case. And galaxies also have quite a spread in size, but again, we understand roughly why they're in that range. And clusters of galaxies have a scale which is determined by the early universe. So we understand how different types of aggregation are explained in different ways. But I think we're not in such a simple universe that everything is just the same. And if you go on magnifying it, you find the same things. And of course, when we get right down to the quantum world, then things get very different. And what, of course, makes the early universe very difficult is that we know that if we go right back to the beginning, we have to worry about quantum fluctuations and about gravity at the same time. The main simplification in the everyday universe is that we worry about quantum theory when we're thinking about individual atoms and molecules, but we don't worry about the quantum fuzziness in the orbits of planets going around a star, because planets are so big that the uncertainty is very small. But when we go back to the very, very early stage of the universe, then in a sense, a quantum fluctuation can shake the entire cosmos. And that's why we do, to make progress there, need a unified theory which brings together gravity and the forces governing the micro world and atoms. So that was one question. And can you remind me what the other question was?
Yes. So is the possibility of the gravitational force get weaker when the universe expands?
Yes.
If you allow me, so also José Eduardo Teres from Observatório Nacional is asking, which are the major challenges, astrophysical challenges, apart from dark energy? So if you want to write it up, sorry.
Yes, okay. Well, of course, the idea that gravity may be changing with time, that's an old idea. In fact, Dirac in his later years pursued this idea. There are pretty good observational constraints on this, because if gravity changes its strength, if it gets stronger, for instance, then all stars get brighter because they're squeezed more by the stronger gravity. And so from looking at stars at all distances, we can set upper limits to how much gravity has changed, and there's no evidence for change. And indeed, if our models are correct, it was the same back when the universe was a second old. Otherwise, the expansion rate would give different amounts of helium. So it's important to check whether something like gravity does vary from place to place. And so there are ideas that gravity does have more complicated changes, and that this may be a way of explaining the dark matter in a different way. I personally don't think those are very convincing, but there are ideas of that kind. And there are also experiments being done. It's very worthwhile to see if there's any evidence that atomic physics changes. I mean, for instance, if the mass of the electron were to change between the young universe and now, then if you took the spectrum of a distant quasar, then you would see some differences in the line ratios from if you took a spectrum of gas here nearby or in the lab. And here again, there are limits of not more than 1 part in a million change in the mass of the electron, and similar for other constants. There are people who've done quite detailed work on this, because it is, of course, very important to see if there are changes in these fundamental constants.
Okay, Professor.
So if you ask about exciting challenges, then I would say in cosmology, there are two classes of challenges. One is to understand the things which are still very speculative, like about the ultra early universe, which needs physics that we don't yet have and can't yet test. That's one thing. But then the other part of cosmology is what I call environmental cosmology, which is to understand in detail how the universe got from its early stage to the present. We understand in outline, we see an outline when galaxies first formed, but we like to have much better observations of how the very first stars and galaxies formed, how this heated up the gas, etc., and to fill in all the details. So that's an endless quest to fill in the details of how that happened. So I would say that that to understand how present structure emerges is something where better observations and better computer simulations are going to help a lot. But I'd like to put in a plug for a topic which didn't really come up in this talk at all, which is exoplanets, because I think if you talk to many members of the public, they would say that one of the most exciting things in astronomy is finding planets around other stars, and even more exciting if they're found to have life on them. And so if you ask me what I think is the most exciting thing in astronomy, it is that within 10 years, we may have evidence for some sort of vegetation or some sort of life on some Earth-like planet orbiting other stars. And if I can expand on this for a minute, we know there's no complex life in our solar system, although probes are looking for some sort of life on Mars, and there may be something simple under the ice of Enceladus, a moon of Saturn, or Europa, a moon of Jupiter. But on the Earth-like planets around other stars, because they're like the Earth, and maybe some of them have had life which evolved rather like the Earth. And the European Southern Observatory's big telescope, the extremely large telescope, will be able to get spectra of the light from Earth-like planets orbiting the nearest stars. It's a challenge because you look at the far-fly next to a searchlight, the planet is millions of times fainter than the star it's orbiting. But if one can isolate the light from the planet and take its spectrum, then there are distinctive features due to oxygen and chlorophyll and things like that. And you could learn other things. I mean, if you could actually look at the planet, which is in Carl Sagan's phrase, like a pale blue dot, then if it's got oceans and continents, then the shade of blue will depend on what phase you're seeing. Just like if you look at the Earth from a great distance, if you look at the Pacific Ocean, you get a different shade of blue from if you're looking at the landmass of Asia. So within 10 years, we will be perhaps doing analyses like that of Earth-like planets. But of course, we don't know whether life is so rare that it only existed here on Earth. It could be it's just a fluke and only exists here, or it could be widespread. And incidentally, that's why it's worth looking even for the dullest and most primitive kind of life elsewhere in our solar system, because if we could show that life had originated twice independently in our solar system, that would say straight away that it can't be something ultra rare and it must exist in billions of places in our galaxies. That'd be a really exciting discovery. So I think observing exoplanets and discovering more of them, we have thousands of them already, that's a very exciting area. It'll be a long time before we can actually get an image of an exoplanet other than just as a faint point of light. But I think, in fact, I say in my recent book on the future that this should be a long-term goal, and we should try and do this by 2068. We should aim by 2068 to have a big enough optical interferometer in space to actually get a sort of resolved image of an Earth orbiting another star. Now, why do I say 2068? That will be the centenary of the famous picture Earthrise, taken by Apollo astronauts orbiting the moon, showing the Earth as a delicate blue surface, contrasting with the moon in the foreground, sterile world. And that became an iconic picture for environmentalists. And if we could have 100 years after that, a picture of an Earth-like planet as a poster, which become equally iconic, that would be a wonderful way to broaden our horizons. So that should be a challenge, I think, for the next but one generation of optical interferometers in space.
Okay, Professor. So thank you very much. Obviously, there are more questions, and there are lots of compliments from the audience, both from here and from the YouTube. We have dozens of people here and there, but I think it's time for us, Professor, to thank you finally for this wonderful moment that you have gave the opportunities for us to experience. So I'll ask as a closure for everybody to turn on their microphones again for a final round of applause in recognition to the professor.